this, but now we have Jim Pinkerton from Microsoft. We're really glad to have Jim. He's a lead architect of Microsoft's Windows Server Group. His primary role is designing private cloud solutions, including networking, storage, fabric, and management at scale. Previously, Jim was lead architect for SMB and CIFS, the world's most widely used file access protocol. He helped lead the development of SMB3, the next gen, which transforms server shared storage from block storage to file access. And he's also been a network architect in the Windows core networking team, working on scalable networking technologies and advanced network device interfaces. Jim has helped create and lead standards in SNIA, IETF, NCT11, InfiniBand Trade Association, and RDM Consortium. Before Microsoft, he was principal engineer at Silicon Graphics. He holds a bachelor's from MIT and a master's in computer science from the University of New Mexico. Please welcome Jim Pinkerton.
So that introduction was a great way of saying, yeah, I'm an old fart. It's been an interesting exodus, walking through the transition in the server community over the last 20 years. I started off after getting a double E and then getting a computer science degree, going off and doing advanced networking, specifically worked a lot around remote DMA and the standardization efforts that was done back in the early 2000s, both in Silicon Graphics and in Microsoft. And then focused a lot around scalable networking. And then from there I transitioned into storage, and for about 8 years or so been focused on storage and solving that in combination with networking with the SMB3 work that we did to create a highly fault-tolerant, highly scalable file access protocol focused on server application storage. And then from there, in the last 2 years, I've been focused around private cloud. What does it mean to take some of the innovations that have been spearheaded in the public clouds and try to take that to the enterprise and to service providers? And as part of that, to me, there was a bit of a dream. To me, there's this wonderful world that we all hear about and on the periphery that says, oh, these hyperscale clouds, the Azures, the Bings, the Googles, the Amazons of the world, have figured out how to use high-volume hardware that's basically highly fault-prone and make a reliable, available service out of it that can scale to a worldwide basis. That's a really crazy goal when you think about it, when you take a step back. But the reality is that technology, the scale that they deploy at, is this crazy scale. For instance, Azure, as an example. When they deploy 20 racks at a time. That's the minimum deployment. I don't know about you, but most of the customers I talk to aren't interested in that minimum scale. They want something that's a little more practical, a little smaller. They'd love to grow to that scale, everybody would. But in terms of starting at that, it's a non-starter. So to me, there's a bit of a dream. If I could only take that efficiency that's been innovated on in hyperscale cloud properties across networking, storage, compute, and management, and be able to apply it to data center. And so just as an example, then let me walk you through some of the pretty spectacular numbers you get out of these hyperscale clouds. Microsoft hosts a lot of cloud scale services that have worldwide reach. Just to give you a feel for some of the numbers, we have approaching 10 billion objects in Microsoft Azure. We have roughly 50+ billion minutes of voice being exchanged on Skype a month. We have approaching 6 billion worldwide queries on Bing. These are really crazy numbers that these hyperscale cloud properties are able to achieve. But again, the problem is the level that they're deploying at is not really achievable by most enterprises or service providers. For instance, on the right side, you can see a picture of some of the containerized solutions that we're deploying at scale worldwide, where you plop down a container. And the reality is those containers contain a really astonishing amount of compute and storage. And that's the minimum deployment size. So again, part of the trick of this, in terms of creating this, trying to realize this dream of taking the hyperscale cloud and moving into the enterprise, is kind of trying to mix and meld these two worlds of enterprise and hyperscale cloud. And to that extent, I would argue that Microsoft is somewhat uniquely positioned to be able to do this, because we can get in the underwear of the hyperscale cloud. We can understand how dirty it really gets. Sorry for the analogy. But it really, failures occur everywhere. Hard disk drives are the single biggest failure mode that causes people to be deployed into the data center in Azure. Hard disk drives. Networking, storage, there's this constant churn of change in the hyperscale cloud. It's not even remotely static. Tons of new resources and capacity are coming online on a monthly basis. Tons of changes in terms of improvements, et cetera. How do you manage that amount of churn and still create a reliable, available, scalable service? Well, first and foremost, we're starting with the foundation, using what we call the Cloud OS. We're using the same hypervisor that Azure and our cloud properties are using. We're using the same user interface, what we call the portal. And so we're taking some of the capabilities that are in our hyperscale properties and delivering that to the enterprise and service provider customers. And then the other side is we've got an interesting set of assets around enterprise. Microsoft has spent a lot of time trying to understand the enterprise customer. And in fact, that's been recognized to some degree by the community. We're in the leaders' magic quadrant in four separate segments around virtualization, around what's called IaaS, which I'll be going through in a minute, PaaS, which I'll be going through in a minute, which are both cloud concepts, and then around public cloud storage services. We spent a lot of time trying to be relevant in the enterprise. And I would argue that as we do this, it will become a world where things go hybrid. People are very focused today on private cloud, taking the cloud technologies and delivering them on premises. But over time, what customers want is to be able to choose. They want to be able to, for the right application, the right data set, be able to deploy on a hyperscale cloud, but where needed, if they want to keep their data local or they have unique computational requirements, et cetera, they want that private capability and they'd like to be able to move back and forth. So hybrid, to me, is also a part of the mix. So that's kind of the dream, but actually before I get too much into the dream, let me take a step back and say, well, what is cloud? There's been several references to the cloud in movies lately, where it's, who knows what it is? It's something up there. I would argue when you map it to the enterprise, it is a fundamental shift. It's a paradigm shift on how you manage and deploy servers. The old world, you would deploy a single server. In cloud, you never deploy a single server. You may incrementally deploy some small number of servers, but in general, you manage and deploy a set of servers. You have some kind of management domain that you operate on, and that management domain, for the purposes of this talk, I'll call it a stamp. And so when you deploy this collection of servers, the paradigm that you manage it in is really important. And what's come out of cloud is that there's essentially three paradigms for how you manage the deployment of this. And it's all around managing the services that your customers want to put on top of the hardware. And so one category is what's called IaaS, or infrastructure as a service, where essentially what we're saying is, well, this is really post-virtualization. Essentially, almost every workload these days has been virtualized. Not quite every, but by and large. And so really, as you go into private cloud, it's really post-virtualization era, where there's a lot more interesting discussion to be had around not just virtualization of compute, but virtualization of storage and virtualization of networking. But in this classic world where you have some application, you want to be able to deploy it as a virtual machine into a private cloud. That's what's called IaaS. And so a VM is owned by this new paradigm called a 10x. And that tenant manages that virtual machine with completely virtualized resources. In the PaaS world, it's a bit more aggressive than that. The IaaS world is typically take an existing set of services and put it on a virtualized cloud and then be able to manage and scale. In a PaaS world, you're being more aggressive than that. You're trying to deploy higher density solutions where you have multiple tenants within the same virtual machine. And so you use containers or some equivalent technology to be able to isolate those independent tenants. But it is in a world where, again, you're tenant focused. And then the last category is called software as a service, where the application itself now becomes multi-tenant aware. So those are the three vectors of this new paradigm shift that's occurring as we talk about cloud, and then try to take that hyperscale cloud and bring it to the enterprise. And I'd argue that's just kind of the high level of how you manage your customers. Really down at the low level, it comes down to extreme computing. I'm an ex-HPC guy, and that used to be the term reserved in the HPC world. And the reality is what the hyperscale cloud folks are doing is extreme computing. It's crazy what they're trying to pull off. They're literally deploying 1 million servers worldwide and being able to manage that at scale. And so on the one hand, you have extreme virtualization. It's much more than just what is the hypervisor. We're actually virtualizing compute, storage, and networking. And so the model then is the customer comes in and they think they own the resources, but in fact they don't. It's highly shared. You also have extreme automation. The cloud implies that you want the tenant to manage the resources, not the hoster, or not the IT admin in the enterprise that's providing these cloud services. And so the tenant should be able to come in, deploy new virtual machines, manage their virtual machines, manage performance issues, manage failure issues, etc., without pulling in the IT admin that actually owns the fabric that this cloud is running on. And so that's a huge difference. It potentially radically reduces the IT admin load that's required through this extreme automation. And so the reality is today, using private cloud technology, you can deploy a VM. A tenant can deploy a VM with no admin intervention at all. And it can be done in seconds. It's a complete paradigm shift from what we're used to, where in prior worlds, a decade ago, to make it really stark, if you wanted to be able to deploy a new service, you had to go buy a new machine, you had to be able to provision that machine, you had to get permission from the network admin to get your IP addresses, you had to get permission from the storage admin to get your storage, and then you had to talk to the service admin to then put that on the new hardware resource and be able to put that all together to actually stand it up. It could take easily months, easily. In this new world, whether it's private cloud or hyperscale cloud, you can do it in seconds to minutes. It's a really fundamental change. The other thing that's fundamental is from the IT admin's perspective. The service provider or the enterprise that wants to deploy this technology, the technology needs to be self-healing is what I call it, fault tolerant. But it's more than fault tolerant. It needs to be able to heal to the point where it has the same level of redundancy that it had before the failure. The basic goal is to make it so that that poor IT admin that's trying to sleep through the night on a Saturday night, when that failure occurs Sunday morning at 2 a.m., you don't want that pager to go off. You don't want him to have to go in and maintain that hardware simply because one failure occurred. In this new world where we're using high volume hardware that can fail, we want that failure to be a yawn. Maybe he gets a page and he looks at it and he says, it's self-healed. Okay, I'll go back to sleep. That's the new model of private cloud. And so that then comes back to this high volume hardware approach, that we want to be able to deploy it on standard high volume hardware, whether that's switches, network switches, compute resources, or storage. All three of these areas need to be high volume hardware. And then lastly, and probably most importantly, the other aspect of cloud that's shown itself is extreme dynamic scaling of resources. And that's the part that I think people tend to miss. The reality is what people want is to be able to deploy a service that takes up minimal resources when no one's using it, and then dynamically scale out as load increases. And so, for instance, in the middle of the night, you have a service that you've just deployed, and it consumes one virtual machine. But at 8 a.m. the next morning, when everybody comes into work, it dynamically scales to 64 virtual machines, etc. That's a key part of cloud. It again gets back to that issue of how do you make it self-managed, rather than an IT admin having to be in the middle of everything. And so, as a result of those goals, you end up with this new paradigm that people are talking about across the industry around software-defined everything. So we start with this high-volume compute hardware, high-volume storage hardware, high-volume network hardware, and then we're going to stitch it all together through the use of software on top to make it so it's reliable, available, serviceable, scalable, all the normal buzzwords. A key part of that, though, is actually the portal, the umbrella software that allows you to manage all of this hardware, or really what we call a fabric now, in a completely tenant self-service way. And so that's the other part that I think people miss when they talk about software-defined everything, is you have to have something that stitches together these software-defined everything. You have to have a portal that allows a tenant to be able to come in and access these software-defined resources in a way that makes it seamless for them to deploy new services. You have to keep in mind that the tenant cares about service uptime. They don't care about the storage, they don't care about the network, they don't care about the compute. The bottom line is, those are necessary evils. They care about service uptime, service scalability, etc. So the portal is key. And then the other side is, the IT admin becomes a generalist. You don't have these separate silos of network admin, storage admin, compute admin, or service admin. It's blended. There's a fabric. And that fabric, as I mentioned, is self-healing. But the reality is you need to repair it to get back to the original capacity that you originally deployed. And so that admin is still absolutely in there. They're just not dealing with every single request that comes in from the tenants. And so what you end up with then, this dream of software-defined everything is virtualized. From the tenant's perspective, they think they own the hardware. They have no idea that, in fact, they're actually being deployed on what's called a virtual core, not a physical core. That they actually have time-sliced bandwidth on the network. That they actually have time-sliced capacity and IOPS on the storage. All of these different areas have been virtualized to make it so that you can tightly pack these tenants on high-volume, very fault-prone hardware. And the reality is when you put all this stuff together, it's actually pretty complex. What we found, and we've been delivering this at scale within Microsoft, is that the network connectivity gets a little interesting to make it so that it's this fault-tolerant interconnect. The storage interconnect also gets a little interesting because you want that very rigorous fault tolerance to be able to be something that's applicable to enterprise mission-critical workloads. To solve that problem, we took a very different approach. We have a suite of software that we provide across Windows Server 2012 R2, System Center 2012 R2, Windows Azure Pack. You can buy independently from us. What we found is that when you try to put it all together, particularly when you're trying to achieve high scale, it's difficult. There's a lot of wires. There's a lot of configuration issues that you have to get through. And so to solve that, what we've done is we've created what we call a cloud platform system. It's powered by Dell hardware. But it creates an Azure-consistent cloud in a box. And so it scales from 1 rack to 4 racks, and you can buy incrementally as your resource needs scale. But it's designed specifically from all of the learnings that we've taken from Azure. And in fact, we've actually provided consistency in terms of the management infrastructure so that all of the work that you've done, that the customer has done to be able to deploy VMs automatically, for example, can now be used in this private cloud. We've also found that one of the other new things about cloud is that they have this concept called site down. I don't know how many people are familiar with this, but in our hyperscale clouds, Site down is a buzzword that says nothing else is higher priority. And so if you have a review with your vice president in the next 10 minutes and someone texts you and says, I have a site down incident, you cancel that meeting. It's the most important thing in the world. You've got to get the site back up again. Downtime is absolutely the worst thing. And as part of that, what we found, we tried to take a very holistic approach to how we deliver a private cloud. We found that support can actually take too long. You want site down to be back up extremely quickly, no matter what the issue is, whether it's a hardware issue, a software issue, a configuration issue, whatever. And so because of that, we've actually taken the approach with this Azure Consistent Cloud in a box, that Microsoft is the single throat to choke. You call us, no matter what the issue is. And we have people that are extremely familiar with this pre-wired configuration, so we can debug it extremely fast. Whether you've configured something that might have caused an outage or however it works out. We also provide a lot of what we call runbooks to make it so it's easy to deploy first-party services, whether it's Exchange, SQL, SharePoint, etc. And then we've tuned it all, built on top of Dell PowerEdge servers, their JBOD storage enclosures, and their networking switches. So the solution is actually pre-packaged, pre-wired. The wiring is pretty impressive. I'll walk through what the network infrastructure is, but it's pretty unique. It's using the standard servers and switches, and then you can see the JBODs are all hot swap, hot pluggable. And so it makes a very nice servicing model. But before I get into the details of the hardware, let me just provide a very brief overview of a private cloud stack. So we start from the bottom with hardware, and I already talked about that to some degree. And then on top of that, we create a software-defined storage, software-defined network, and software-defined compute. For software-defined storage, we're using a combination of SMB3 for remote access, and then storage spaces for reliable, available storage. For the software-defined compute, we're using Hyper-V. And on software-defined networking, we're using Hyper-V network virtualization. And we actually then use a lot of offloads in these to make these things scale extremely well. Built on top of that, then we build a fabric. So we've got the software-defined everything. And then on top of that, we have a set of software through System Center, so that that then allows us to be able to, one, deploy and manage failures, but more importantly, through the tenant portal, this automated interface allows the tenants to come in through the top with the Windows Azure Pack portal to be able to then automatically deploy VMs. And what's interesting then, when you look at how this actually works then, we actually, if a customer comes in and wants to deploy a VM, we will automatically allocate storage, plumb the virtual machine, what we call a VHD. On top of that, we'll automatically plumb the virtual network, so we have complete tenant isolation. And we'll plumb we'll grab from the resources, the appropriate compute resources to be able to deploy however many virtual machines that they need. Completely automated. On top of that, what we found in talking to enterprises is they need a lot more than just that. The core capability of being able to deploy virtualized resources, that's wonderful. But the reality is things like disaster recovery, things like backup are critical for them to be able to deploy any real services. And so that's also incorporated in it. So what we end up with this hardware, if we're only deploying what I call extra small VMs, is you can go with a single rack, goes up to 2,000 VMs, and with 4 racks you can go to 8,000 VMs and 1.1 petabytes of actually usable storage, reliable storage. This is a picture of the actual rack. A little tough to see. The numbers here are kind of fun. Within a single rack, we have 512 cores and 8 terabytes of RAM, 262 terabytes of usable storage. What's really fun is the network interconnect. Within the rack, we have 1,360 gigabits per second of connectivity. Going off rack, which is typically where most people's solutions fall down, we have 560 gigabits of connectivity. So the suckers are a bit of a behemoth on the network side. And in the words of one of my colleagues, It weighs about the same size, about the same amount as a small elephant, 2,300 pounds. Interesting facts. And then it consumes about 17 kilowatts of power. So let me just take a moment then to dive a little bit more into what are the components of the design that are derived from Azure. And what are the components of the design that we decided we couldn't take straight from Azure? We needed to customize based on our experience of what the enterprise and service providers want. I've already talked about the hypervisor. It's really kind of, this whole architecture is post just hypervisor. And that's been developed the last decade. It is kind of interesting as a footnote to say that we've virtualized every workload, including the management workload. And so all of the fault tolerance, all the scale, all the dynamic scale that we've created is equally applicable to the management infrastructure as it is to the tenant infrastructure. And I've already talked about the IaaS and PaaS that we've got the Azure portal there so that the tenant experience will be exactly the same whether they go to the Azure public cloud or to your private cloud that's on premises. And so they'll be able to use the same programming APIs to be able to automatically deploy new resources. And then we also provide a PaaS solution in Azure websites, so that we have very high density websites as part of this. But there's also kind of architectural learnings that we found from our Hyperscale cloud. One is they are laser beam focused on efficiently using hardware. For them, stranded capacity is terrible. It goes right to the bottom line, particularly in the world where these hyperscale cloud guys are, I mean, it's a very competitive environment right now for cost of VM and cost of storage. And so they pay blazing focused attention on how efficiently they can pack their virtual machines so that all the CPU cores and memory are used. Amazing focus on how to efficiently pack their storage so all their storage resources are used. And then they also use state-of-the-art network offloads because they realized that networking can be a key bottleneck. If you end up, for instance, using a ton of CPU resources to get over the network, well, that's fewer CPU resources you can use for the service. So it turns out there's a variety of network offloads, which I'll walk you through shortly, that make that very compelling to be able to pack your virtual machines even more tightly. And then the other major area is the whole being able to dynamically scale. That's what I think a lot of people miss when they talk about private cloud or software-defined everything, is that dynamic scaling is critical. In this world where load changes radically moment by moment, one approach is to provision for the maximum load that you might incur, and then you're kind of stuck because maybe 8 hours of the day you have that maximum load, and the other 16 hours of the day you're not able to use those resources. And so part of what we found with private cloud is that we want to be able to leverage that knowledge about how we dynamically scale that was originally created by the hyperscale clouds. So we want to be able to dynamically scale VMs. We want an integrated load balancer. For the case of CPS, we have a hardware load balancer that is, again, automatically configured when you want to deploy a new virtual machine. And so through programmatic interfaces, you can specify the set of networks you want to have. You can specify in a dynamic way the number of virtual machines that need to be tied behind a load balancer, etc. And then lastly, you want to be able to incrementally scale hardware. As you fill up one piece of hardware, you want to be able to incrementally scale that up to some level. And in the case of CPS, we will incrementally scale it up to 8,000 VMs and 1.1 petabytes of storage, reliable storage. So just to kind of anchor some of those concepts, the way that we efficiently use our hardware resources is we want to pack things as much as possible. And so in general, when you do what's called bin packing, you want to be able to bin pack across as large a set of resources as possible. Traditionally, if you look at how the enterprise traditionally has been deployed, they use a top-of-rack switch that then connects to some kind of director class switch. And the top-of-rack switch is pretty cheap. The director class switch on a per-port basis can be seriously expensive. And so they typically have very limited bandwidth going between racks, which causes you to be able to try to optimize when you're placing new services that have multiple virtual machines and storage. You try to co-locate them to make them very scalable. And the problem with that is you end up with stranded resources. You're not able to pack things as efficiently as you could have if you can pack it over a larger set of resources. Now in Azure, we do it over 20 racks. It's maybe a little more than what most people need. In CPS, we scale up to 4 racks. And we do that by a new technology that was created originally with a partnership with Microsoft Research to be able to create what we call a flat network. And a flat network is defined basically as if the in-rack bandwidth is X, if it's truly flat, then the ratio of in-rack bandwidth to off-rack bandwidth is 1:1, so it's also X. So in a truly flat network, if you have, say, in this example, 1,360 gigabits per second of in-rack bandwidth, you would have 1,360 gigabits per second of off-rack bandwidth. That's honestly overkill. The analysis we've done for first-party workloads is you don't need that much. And so for CPS, what we've done is the off-rack bandwidth is actually 560 gigabits per second, which if you think about it, that's a crazy amount of bandwidth. When you think about trying to deploy that, the traditional way to deploy it would be to use a director class switch, which makes it cost prohibitive. If you actually do the math, the numbers there just basically don't match up. And so that's part of the trade-offs that the hyperscale clouds have already gotten through is how do you deploy something like this that makes it so that you can place your virtual machines anywhere you've got resources available. And so across these 4 racks, for example, I might be trying to deploy 10 VMs, and I can deploy them anywhere where there's resources available. And the storage that is associated with them, I can deploy anywhere that I want. And to be able to get off the virtualized network, I can deploy that gateway service anywhere I want. And so it allows you to be able to pack things as efficiently as possible. And then the flip side of it is by using a technology called equal cost multipath routing, ECMP, we're able to do this with just top-of-rack switches at that layer 2, at that aggregation layer. And so that makes it extremely cost-effective. Yes, you end up with a few more wires, but in terms of the benefit you get out of it, where you have these very high-cost compute nodes with quite a bit of RAM, you're now able to very efficiently pack your virtual machines and not worry about where things lay. Wherever resources are available, you can use them. Another aspect that I previously talked about was dynamic scaling. And so just to kind of make this a little clearer on how we do this. So with CPS, we start with a hardware load balancer in front, and we have virtual machine manager is tied into the portal to be able to automate deployment of resources. And so in this simplistic example, we have a single virtual machine that says is the web tier, and then we have on the back end of that 2 nodes or two virtual machines that are the database tier. And by simply, as you deploy these VMs, set up a very simple configuration option, what we call instance count. In this case, I'm showing instant count can be a minimum of 1, a maximum of 5. You can either manually or fully automated be able to detect when you have bottlenecks, and for instance, automatically deploy additional VMs to be able to handle the load. And this works on every tier. And so it makes it extremely easy with just a simple command line to be able to say, I want dynamic scaling. And when that happens, Virtual Machine Manager automatically reconfigures the hardware load balancer, automatically brings up additional virtual machines, automatically connects the virtualized network to all these different systems, and then bing, you're up and running with no service outage. So those are some of the learnings that we've taken from the Hyperscale cloud, creating this Azure consistent cloud in a box. But that really wasn't enough. In talking to our enterprise customers, they had some unique issues that were really top of mind. First, we wanted to create extremely low operational overhead. And in talking to our customers, what we're finding is patching actually is a ton of time for them, and it actually creates outages. So both of those things are kind of antithetical to a private cloud-based solution. And so what we created with CPS and are also delivering broadly to the market is transparent patching. And so you're now able to patch all of the fabric, whether it's a driver issue, a firmware issue, a BIOS issue, an OS issue, an application issue. Any of those issues, we can online patch them by shedding load off the particular node that you're patching in a completely transparent way, and then moving the load back on those nodes to keep the service up and running, while you then go through all of the systems in your private cloud. I've already talked about integrated management, but the other part is integrated testing. And so what we found is a lot of these private cloud solutions aren't actually tested at scale. It's kind of a do-it-yourself kind of an effort. And it's actually extremely difficult to get this stuff to scale properly, to make sure that, well, yeah, you throw in the lab and you get it to run on 4 or 8 or 10 or 20 machines, and now we want to deploy something real, and you start finding issues. So we took a completely different approach. We re-engineered how we develop Windows Server so that we no longer use physical hardware. We always deploy in a virtualized environment. We have a collective virtualized environment called Nebula, where we're today deploying 20,000 VMs a day on top of the CPS hardware. And so that's one heck of a metric for us. We won't ship the next version of Windows unless CPS is running reliable at scale. As part of that, so we, on the one hand, now also have the ability to pre-qualify all the patches, so we can deploy them internally at full scale, 20,000 VMs a day being deployed. But the other is failures. So we wanted to be able to ensure that customers, when they deploy this, can be comfortable that all of these failure modes are in fact fully tested. And so what we did is we created a pile of software that we call the Private Cloud Simulator, with the express goal of trying to simulate basically a year's worth of failures in 7 days. And so we go through an amazing variety of things. I'll walk through in the next slide some of the variety of things we do. But the intent is the entire storage subsystem, the entire networking subsystem, all of the portal, everything is under full load. And then we intentionally go in and start shooting things in the head. Whether it's a compute node, whether it's a network switch, whether it's cables, whether it's hard disks, whether it's JBODs, etc. That's a critical part of delivering something that an enterprise or a service provider can actually use. It needs to be tested. The other side that we've heard from customers is to be able to reduce the size of the private cloud that you want to be able to deploy. The path that the hyperscale cloud guys are doing, this aggregation of storage and compute, so that your minimum deployment is actually 40 racks, 20 racks for storage and 20 racks for compute, doesn't work for that. They want to see storage, compute, and networking in one rack. It's converged. And then also, in terms of the fault nodes that I just started walking through, we're extremely formal about the fault nodes. And so we have what we call N+2 fault tolerance on certain components that fail reasonably frequently, because we have all the data from our Azure Hyperscale partners. And then for some things, like network cables or network switches that fail less often, we have N+1 fault tolerance. So you can accommodate one failure and lose and don't have the service go down. So just to kind of show that, I'm showing kind of a theoretical version of CPS. It's think of it as a compute set of resources, a file server storage set of resources, and on the back end of that, a bunch of JBODs. And so what we do is we actually go through and we shoot all these different components in the head under full load. And so whether it's hard disk drives, as I mentioned previously, are one of the most frequent sources of failure in our hyperscale cloud. So we do what we call N+2 fault tolerance there. We can accommodate 2 disk failures with no loss of access to data. For server nodes as well, we've seen that they actually go down with some frequency. So we also do N+2 fault tolerance there, whether it's a storage node or a compute node. And then for things that fail less often, like cables, we can accommodate a single failure if we have a fully fault-tolerant network infrastructure, the switch A, switch B, so a switch can fail and everything will transparently fail over with no loss of service access. Then the other side was converged. Being able to put both storage and compute and networking in one rack and be able to scale that appropriately. And so what we did with CPS is the bottom half of the rack is storage. It contains 4 JBODs, a total of 240 disks, with 4 storage nodes. On the top half of the rack, we have compute, a total of 32 compute nodes, each with 256 gigs of RAM. And then at the very top of the rack, we have all the network switches. And so we have a management network, so that the fabric management can be done through out-of-band management, through the BMC, as well as this flat network that I was mentioning before, to make it so that you scale very nicely. And so the way we've thought of this then is we have very tightly constrained fault domains. And so we've defined everything in terms of scale units. And so as we add racks, again up to 4 racks, we then manage them as scale units. A compute scale unit or a storage scale unit. And out of those scale units then we carve resources. And so we carve storage out of the storage scale unit, and then in the compute scale unit, we actually carve independent resources for the management that I talked about previously, the what we call the network edge, which takes you from this virtualized network onto the physical network to be able to communicate outside of the stamp, and then the tenant compute resources. And then of course we then scale that across all of the 4 nodes. So it gives you some feel for our approach of taking Azure's model of hyperscale and mapping that into an enterprise environment, and what we hope and expect to be extremely relevant to enterprises as well as service providers. What's interesting though is the world never stands still. And so when you look at what we've delivered in terms of CPS today, that hardware I believe is pretty cutting edge. But the reality is our public cloud is continuing to innovate. And so you'll see this afternoon in Kushagra's talk, he'll be talking about the next generation hardware that our public cloud is creating, and that we've just contributed to the open compute platform. It's what's called the Open Cloud Server. That hardware, when you start looking at some of the advances that are coming out in the hardware industry, is highly relevant as we continue to march down this path of software-defined everything. So whether in the storage area, moving to an NVMe or even potentially NVDIMM infrastructure to get that higher IOP, moving to these much higher capacity hard drives, 5.25-inch hard drives are even being talked about by some, extremely high capacity storage. On the networking side, moving all of the CPS infrastructure is focused on 10 gig, because that's to us the knee of the curve and the price point for networking. But our hyperscale partners are buying a substantially larger volume than the rest of us, and so they're able to push the envelope and move into 40 gigabit networking with new offloads. You'll see, for example, we have an FPGA offload that's being shown in our booth, just to give you a feel for some of the really advanced offloads that are being looked at. Potentially new network topologies, certainly next generation isolation in terms of how you pack these virtual machines. And so a lot of the learnings that they're creating, they're continuing to push the edge. And that's the wonderful thing about being able to align behind something that's at this hyperscale, is that new technologies continue to march down the path, and being able to deploy them at hyperscale and understand how well they work and how well they don't work, and what their issues are and how to overcome those issues to make them any failure modes or any isolation issues, gives us great insight into those issues. They're also looking a lot around RESTful management. There's a lot of fairly interesting work going on within the DMTF around what's called Redfish, around RESTful-based management for chassis management and for node management. So there's a lot of different areas that are continuing to innovate in the hyperscale cloud that we also expect to then pull into the on-prem enterprise focused service provider-focused private cloud. And with that, I'm done. I suspect we have time for some questions. Yeah.
Just talk later presentation. When you have saving all the extensibility that you talked about, how do you test it other than the actual source data, like in a simulated controls, and full stress test for different parameters to show that you have all that and better than
Yeah. So the question is basically how do we test this to show that in fact it works? And so testing. So there's many different environments you need to put together to be able to make the thing work. And so one is after a controlled environment where you have very controlled parameters. But honestly, the other side is you want the big bad west of actual real workloads running. And so we've done the gamut. So we do everything from feature level testing to ensure particular components are working well, all the way into this random failure mode testing where we're running everything in full out, and then we just shoot everything randomly and expect it to recover, all the way then to the Nebula test infrastructure where we're deploying 20,000 VMs of essentially customer VMs. That is all of our test teams across all of Windows, but it's a massive at-scale test. It's mission-critical test. So it allows us to be able to monitor how well we're actually doing, and also being able to work with the IT admins that have to keep the thing up. Yeah.
You mentioned Microsoft Research. Just tell us a little bit more about what the role of Microsoft Research was in helping develop.
So the question was, what kind of role has Microsoft Research played in developing these technologies? They've been a very close partner of ours in many ways, some of which have come above water and some of which hasn't. And specifically here, back, I think it was probably 4 years ago, we were looking at how to more efficiently bin pack all of these resources in a hyperscale cloud environment. And what we found was that bottleneck that I outlined with top rack switch, the off rack bandwidth. And it turns out back 4 years ago, there was a lot of different paths we could have gone down in terms of network topology to create something that was scalable and also highly fault tolerant. And what was originally done was what was called a layer 2 flat network to be able to create that scalability. And the problem with the layer 2 flat network is you have these issues around multicast and broadcast storms. And so there was a lot of research done around how to create this flat network, and in the end it was realized that a layer 2 flat network, in fact, was completely the wrong approach because you can't isolate fault domains. And so what was done then finally, again through research, was moving to a layer 3 fault domain where we're built completely on top of BGP with this ECMP capability to make it so we have completely independent fault domains between the different racks. So that's one area of research. We've also done a lot of research around costs, partnering with Microsoft Research. They've actually got some very, very interesting technology out here that you might want to check out around cold storage as well. And so there's a lot of different areas that they're pushing the boundary for us in a maybe more aggressive way than a normal product team can develop. One of them that I think is possibly the most interesting is being able to deploy FPGAs into the server nodes in the hyperscale environment. And they've got that demoed out there as well.
Yeah, you were talking about layer 2, layer 3 network in the top of rack solution. You guys are using SDN. How are you implementing that with that to possibly get rid of the routers and the switches and putting it into one unit for SDN?
So the question is, how are we doing SDN? Just to give you a little bit of a feel for it. So one of the, again, learning from Azure, we wanted to be able to deploy new virtual machines without a lot of configuration changes in the network. That's one of the biggest source, the worst case outages that you can have. If you screw up a reconfiguration of the network, man, a lot of things can go down really, really fast. And so what we wanted was something that was pretty static in terms of the network configuration, but would still allow us to be able to deploy these new virtualized networks. And so what we use is a thing called Hyper-V network virtualization. And traditionally, what we've seen is that actually creates some hot cores in the compute infrastructure. But by using what we call NVGRE task offload, that allows that overlay network that's part of what network virtualization implies. Actually, let me take a step back. So when I talk about network virtualization, pretty much everyone is taking the path of what's called an overlay network. And so you have the physical network, and then we're going to virtualize it. And so you create a second network on top, and that's the tenant network. And the tenant network then is what needs to be deployed in a very dynamic way. And you have all the fun stuff around isolation of workloads, as well as being able to dynamically bring up and down this what's called edge connectivity, to be able to then allow that virtualized network to talk to the outside world. And so the way that we do it for CPS is we use NVGRE task offload in NIC to make it so that we get the same level of performance you would natively. So we're able to get 18 gigabits per second VM to VM between any two VMs in the stamp. And then going off stamp through this edge gateway, we have various edges. And so there's a NAT edge, a forwarding edge, a site-to-site edge. And of course, they have different performance characteristics. The site-to-site does encryption, for example, so it has quite a bit of CPU overhead. But in general, we get somewhere between 3 gigabits per second and 10 gigabits per second per edge gateway total bandwidth through it. And so total aggregate throughput through the stamp is roughly 60 gigabits per second off stamp. And then when we deploy new VMs, we're not actually changing the ECMP network, because the ECMP network is static. It's a physical layer thing, layer 3, but it's a physical layer. It's that bottom network. When we wanted to be able to deploy a new virtual network, that BGP routed flat network stays exactly the same. And then what we have to then do is plumb through the virtual switches, new switch configurations, and then plumb to the load balancer, new connectivity to the virtual machines to be able to do that dynamic scaling that I talked about. Does that answer your question? The question was, is it mostly done in DNS? And no, not at all. It's a bit more fun than that. Yes? The question was, sorry, the list price on the small elephant. I'm a technical guy, not a marketing guy. I would suggest though, go to Microsoft.com/CPS, and there's a paper there that walks through some comparison of competitive solutions and what our list price point is. So I'll let you do that offline if that's okay. Go over there.
Yeah, avoiding this stranded storage capacity, super interesting. Is there a hardware reference guide or a runbook that's available that helps us in the industry understand how it's done?
What you might want to do is attend a talk this afternoon where we'll be walking through the storage component in CPS.
Awesome.
That's probably the best way to, there's a rich set of discussions we can have on that.
And follow on really easy. You talked about failure mode testing, hitting the red button, pulling the drives.
Yeah.
Are those test results available?
So the question is, are the test results available for the fault mode injection that we were doing? What do you mean by that? I mean, so our goal at the end of the 7 days is zero tenant visible errors, and we won't ship unless it's 0. So I don't know if there's any results necessarily needed, other than, yeah, we did it.
Let me qualify my question then. If you pull a disk drive, that's going to have some impact. It's going
Yes.
to slow something down.
Yes, absolutely.
Totally.
Totally fair. Yeah, and so there's, for those that are more storage focused then, if you think about how storage works, when you start making these components fail, you have to then rebuild. Keep in mind that the goal here is self-healing. And so if you've got 3 copies of data, for example, and you lose 1 copy, you'd like to be able to regenerate that copy, right? And get back to that those three copies. What we do in CPS is we do it in parallel. And so we don't use what's called a hot drive to be able to rebuild, which creates bottlenecks. It's massively parallel across the 240 disks that we have in the storage scale unit. And so because of that fault actually has minimal overhead. We haven't yet published the numbers, but it's actually astonishingly small because of that massively parallel rebuild. Yeah.
Questions in few areas. In your converged system architecture, from the standpoint of a whole platform, are you considering increasing the density of the compute trays with what might be termed as microservers? I don't know if you would describe it as a microserver now. That's one question, because highly dense compute makes sense in your standard platform architecture as it exists today. How, why, what, where, and not why. Also, the second question, now on the software side, a lot of highly dense disaggregated racks with Linux. You have the number of software startups that are trying to do the same sort of management tools in terms of orchestration and provisioning. How do those Linux environments fit within the Microsoft structure for one hardware, one software?
Sounds good. So I'd like to take the second one first. So in terms of Linux and our support for it, we're actually one of the top contributors to the Linux kernel. We spend a lot of time making sure that it works well on our virtualized infrastructure. Linux VMs are fully supported. Everything that I just said applies equally to Linux VMs as well as Windows VMs, just to be clear. And so on that side, we're fully embracing the open source community. In terms of microservers, honestly, we're still evaluating. What's been interesting for us is the density that we have with CPS is roughly 17 kilowatts. And we're finding internationally that there's certain regions of the world that actually don't like 17 kilowatts. They want more like 8 kilowatts. And so the density is arguably too high. And you can solve that potentially with microservers. And you can certainly argue that in this brave new world where we have a cloud paradigm, where all that really counts, if you look at kind of the new way to show your skill numbers in a cloud environment, our top level isn't how many servers I have, it's how many cores I have. It's not how many gigabytes I have per server, it's how many total terabytes of RAM I have in the system. It's not how many individual storage nodes I have, it's what is my usable storage. It's reliable, available, scalable. And so in that world, you can certainly argue this plays well to the microserver. That as the microserver becomes faster, it really comes back to what is the computational resource requirements of a VM in terms of the number of virtual cores. And you can argue that most of the VMs are 2 to 8 cores, and so maybe that works pretty well. What we've seen, though, is that theory doesn't quite map to reality. It's still kind of in its infancy. So we're watching it closely, but it's still early.
Actually, I have two questions. One is how do you scale between the on-premise private cloud and your Azure public cloud? And that's for the software solution, that would be nice to know. Second question, why do you start for that? Do you have any plans to beyond for that?
Okay. So the first question was, what's the interaction between the public cloud that we have, Azure, and the private cloud? There's two areas. In the brevity of this talk, I didn't get to them. So we have a service that actually monitors the private cloud that runs in Azure. And so that service allows you to, across multiple of these CPS boxes, be able to aggregate up a better understanding of what is actually happening across all these different stamps. And so through that portal interface, you can actually deploy what we call canary VMs and do canary operations, and then be able to aggregate, do data mining through pushing events up into Azure to be able to do data mining to understand how your cloud is actually performing or if you've got any issues. Another area is Azure Site Recovery Services. And so that's also fully supported in CPS. So if you have 2 CPS stamps, you can do disaster recovery between the 2 stamps and you use Azure as the coordinating entity. The data does not go through Azure. We're honestly very sensitive to the issue of data provenance that some of our customers have. And so, at least for this first version, we are not pushing data into Azure. We are enabling, though, that private cloud between 2 different data centers to be coordinated for disaster recovery purposes in the cloud. All right, did I answer both, or I got one of them?
The second question is, you mentioned that you stop at 4x for the CPS.
Yes.
How do you have plan scale beyond 4x, or why do you stop at 4?
Well, we're not at this time announcing future plans. This product was just announced about a week ago in Barcelona. The core capability scales much beyond 4 racks. It is derived from Azure's scale points. The reality, though, is we're still getting a feel for what customers want. And so we want to be very focused on what customers want. And so if customers come in and want something bigger, then we're happy to chat. But at this time, we're only supporting 4. Sorry, in the back there?
What was the need to accelerate certain functions of that features? What functions went up here?
I was not directly involved in that work, but the good news is we've got Microsoft Research physically here in the showroom floor out there, and they're happy to walk you through it. The very short answer is what they showed is excellent scaling of Bing search results using an FPGA accelerator. So yeah, please go talk to them. It's very interesting work.
Okay.
Yes.
Jared Murthy, because you did not say that there's no independent stress testing done, to see elasticity and functionality of clouds, is it not a good idea to have an industry-wide independent body to analyze, test, whatever it takes to do, by injecting particular traffic, and then verify these multiple parameters, so that single company cannot say we are better than the other.
So I think the question is, what role is open standards around fault injection?
And government open stack performance testing and stress testing. That's more important.
So I spent a good portion of my life working on open standards. And to me, there's aspects that really are amazing around open standards, and there's other aspects you've got to be a little bit cautious. I would argue the fault insertion is highly implementation dependent. And that's the one area that to me is very difficult to figure out how to map into an open standards environment. We went into the shorts of how the storage works, how the networking works, how the compute works, how the management infrastructure works, and made sure that we looked at all the race conditions and hit the worst ones and then made it fail to make sure that it would stay up. That's highly implementation specific. In terms of perf and scale testing, that to me is a much more interesting path. Particularly when you start looking at performance testing, I would argue that a lot of the performance tools that have been created are basically leftovers from the 2000s. It really doesn't map into the cloud. When I gave a talk in Spain 2 weeks ago on this, I actually walked through a new tool we have called disk speed. One of the things that changes fundamentally when you go with private cloud is that everything can be oversaturated. And so, to me, it's just not acceptable to publish performance results without publishing where your saturation point is. And so that's what this open source tool is. What we did is we contributed to GitHub an open source storage performance tool that allows you to trivially then see how various queue depths can affect saturation of storage and be able to get the latency variance, which is the key issue in private cloud. You want to be able to track that 95th percentile on your latency variance. And so I would encourage you to look at that disk speed tool.
From the customer's perspective, the interaction.
Yeah, makes sense. I think I'm being pulled off the stage. Thank you very much.
Not that we want you to go, but you have to be exhausted. I just wanted to say a special thanks thanks to Jim for being here today and also for filling in for Tom Bradicich, who became ill and was not able to join us. So a special extra round of applause to Jim. And Jim will be here the rest of the day in the Great American Meeting Room 3, the storage, software-defined storage track. See him there. And also, as he mentioned, the Microsoft Research booth is in the exhibit hall. Please join us.